So today's topic in our unit Matter and Chemical Change, this is topic 3, what are elements? So we're going to go through a little bit of history here. All right, so a little bit of history. So ancient Greek philosophers thought that all matter was made out of fire, water, earth, and air, which were called the four substances or elements. Then we had these alchemists come about. They were part pharmacists and they were part mystic, and they did a lot of hands-on investigations of matter. So they started developing many useful procedures such as distillation. But keep in mind, back then they were very secretive and they also had secret codes just to keep things private from other alchemists and other scientists that were searching the same things. The current view of elements began to develop several hundred years ago. So we have Sir Francis Bacon from 1561 to 1626. His theory was that science should be built on experimental evidence rather just on thought. Then came Robert Boyle, who started adding on to what Sir Francis Bacon said, and he recognized that elements could be combined together to form compounds. But he didn't identify which materials were elements and which were compounds. And these ideas, as they progressed, led to a widespread search for elements. So scientists started to learn that they can start breaking matter apart. They can break it apart until it couldn't break down any further. So things they were using back then were things like heating, burning, mixing, and cooling. So what they were able to find was if a substance was able to break down further, it was a compound, but once it wasn't able to break down any further, it was an element. So they were able to tell if a substance was a pure substance or a mixture. All right, so here we have Antoine Lavoisier, 1743 to 1794. So he defined elements as pure substances that cannot be decomposed, meaning broken down into simpler substances by means of a chemical change. And this definition is still used today. So Antoine Lavoisier's definition of elements being pure substances, it is still used today. And he was able to identify 23 pure substances as elements. His most successful technique was what we now call the law of conservation of mass. So what he did was he took careful measurements of mass. He measured the mass of all the substances that were involved in a chemical change. And what he saw was that the mass before a reaction took place was the same as when the products were formed. So this here is the law of conservation of mass. So anytime there's a chemical change, the total mass of the new substance, shown here as the product, is always the same as the total mass of the original substances. So whatever we started with. So here in this example, we have coal. Coal, if it's completely burned, we have this substance here at the end. But what we're observing here is that we had 100 grams starting with, and we're ending with 100 grams as well. The other thing to note here is the cover on top of the scale to show that any gases that were released are also trapped. All right, so this end product includes any gases that are formed as well. All right, so that's a very important law here, which is called the law of conservation of mass. All right, so our second law is called the law of definite composition. So Lavoisier's emphasis on measuring mass, it inspired other scientists to decompose compounds into elements and to measure the mass of each element. And as this was occurring, it led to this development of the law of definite composition. What this law states is that compounds are pure substances that contain two or more elements that are combined together in fixed or definite proportions. And this will make more sense when we look at examples here. The common example I always refer to is water, because most people know water is H2O. So anytime we see water, whether it's a gas, whether it's liquid water, or if it's ice, it's still water, and water is H2O, meaning there's two hydrogens and one oxygen. Another common compound you guys are familiar with is carbon dioxide. We've learned about carbon dioxide, for example, in photosynthesis. So carbon dioxide is always one carbon and two oxygens combined together. Here's one we're not so familiar with. This is nitrogen oxide. We have one nitrogen and one oxygen. Here we have nitrogen dioxide, one nitrogen and two oxygens. Okay, this diagram here is showing how we can see two different compounds, but each has a definite composition. So if we take one carbon and one oxygen, we form this molecule called carbon monoxide, or CO. And then if we have carbon plus two oxygens, we form carbon dioxide, which is CO2. All right, so one method we're going to talk about here is called electrolysis, which is a process of decomposing a chemical compound. And it's done by passing an electric current through it. So for example, if we were trying to break apart water, a molecule of water, we know it's H2O. If we wanted to break that apart into hydrogen and oxygen, we could use this process of electrolysis. So scientists in the 19th century, they developed this voltaic pile, which is a device that we now call a battery, and they used this to pass electricity through water. And what they found was hydrogen gas and oxygen gas was produced. So scientists started to use electrolysis to isolate elements like potassium, sodium, magnesium, calcium, strontium, and barium. All right, so we are going to start looking at some particle models, but I'm going to pause it here. So we're going to start by talking about John Dalton, so 1766 to 1844. John Dalton spoke up about the particle model, and he said that the particle model was not able to explain everything about pure substances. Properties of water, which is a compound, are different from the properties of the elements that make it up, the hydrogen and the oxygen. So the particles of water, therefore, must be different from the particles of hydrogen and the particles of oxygen. So he realized that the particle model of matter cannot explain particles of different substances combining or decomposing. So he came up with his atomic theory, which we call Dalton's atomic theory. His theory states that all matter is made up of small particles called atoms. These atoms cannot be created, destroyed, or divided into smaller particles. Next, all atoms are the same if they're of the same element, so they will be identical in mass and size. Atoms of one element are different in mass and size from the atoms of other elements. So like how we compared oxygen and gold earlier. And lastly, compounds are created when atoms of different elements link together in definite proportions. All right, this is his model. He thought of atoms as billiard balls. He pictured water with equal numbers of smaller hydrogen and larger oxygen atoms. And his model eventually led to more accurate definitions of elements and compounds. So what we know now of elements and compounds is that elements are a pure substance made up of one type of particle or atom. Each element will have its own distinct properties, which cannot be broken down into simpler substances by means of a chemical change. And we've also talked about compounds. We know that compounds are pure substances that are made up of two or more elements chemically combined together. So Compounds can be broken down into elements, again by chemical means. So we started off with looking at Dalton's model, which looked like this. He just thought of them all as billiard balls. So next came J.J. Thomson, and his model was called the plum pudding model. So what he was doing was he was studying rays in gas discharge tubes, and he inferred that the rays were streams of negatively charged particles called electrons. So he was the first to start talking about electrons. So he reasoned that there must be positively charged particles as well, because atoms don't have a charge. Atoms are neutral. So he pictured all these negatively charged electrons stuck in this positively charged mass, kind of like a raisin bun. So these little raisins inside represent the electrons, and then that bun as a whole represented like a mass of a massive like positively charged, just a mass. All right, and his is called plum pudding model. It's also called the raisin bun model. All right, but again, it wasn't correct, so scientists kept going with the theories and the models. So next came Ernest Rutherford's planetary model. So he hypothesized that almost all of the mass of the atom was in the center of the atom here, which he named the atomic nucleus. And he said that the rest of the atom was mostly empty space occupied by these very small electrons. So the name proton was given to the positively charged particles making up the nucleus. He also predicted that there was one other particle in the nucleus along with the proton, but it was years later, it was James Chadwick that proved him right years later. So Chadwick discovered neutrons, which are uncharged particles that are also found in the nucleus, and it's got a mass slightly greater than protons. All right, so now we have discovered electrons, protons, and neutrons. Okay, so next, after that, we have the Bohr's atomic model. So Niels Bohr studied with Rutherford, and he pictured the atom like a miniature solar system. So like that video showed, kind of like a planetary model. And his model showed that electrons rotated around the nucleus. So here's the nucleus, and you have these electrons rotating around the nucleus. He refined his model and suggested that electrons move around the nucleus in fixed pathways called electron shells. All right, and we have the electron cloud model, and we talked about this. We saw this in the video. It's the most recent accepted model, the electron cloud model. So Louis de Broglie, Erwin Schrödinger, and many others contributed to the electron cloud model, which state that electrons have distinct energy levels, but there's an area around the nucleus where electrons are most likely found, and that's called the electron cloud. And most likely, electrons are going to be found closer to the nucleus than farther away.